so the announcements for today are you guys have quiz number 3 in recitations this week. I guess one section has already had that this morning, and the rest of you are going to be later today and tomorrow. And then Sapling Chapter 20, hopefully you saw that I pushed the due date forward to Friday at 9 a.m. because I didn't quite wrap up Chapter 20 until Friday the week before break. And then Chapter 21, I'm going to finish up in lecture today. It's pretty short. So I'm setting the due date for that to be Wednesday, 9 a.m. next week. Any questions about those? Okay, cool. Alrighty, so I guess if you missed last lecture and haven't watched the lecture capture yet, where we're at is sort of halfway through Chapter 21. We're looking at, I guess we finished looking at hydrolysis, so taking a whole bunch of acid derivatives, turning them back to the parent acid. Now what we're looking at is like going back and forth between different acid derivatives. So we saw a bunch of acid chlorides last time, and just to sum that up, pretty much, since acid chlorides are more reactive than carboxylic acids, a lot of the time, your easiest option for getting to like any acid derivative pretty much is just make the acid chloride and then you can go to any other derivative. Because it's sort of like if you're looking at energy levels, here's the acid, here's the acid chloride. So you're like going up in energy or losing stability by doing this, and then you can like coast downhill into like whatever other acid derivative you want to make. It's going to be lower energy than the acid chloride though. So it's sort of like we're pushing it up the hill and then letting it like go to whichever derivative we give it the other materials for making, if that makes sense. Okay, so that's kind of what the last lecture finished up on. Today we're going to look at something very similar to chlorides, so anhydrides. Okay, so they're similar to, obviously they're similar to anhydrides. Okay, similar to chlorides. So again, since we can make anhydrides pretty easily from the acid, and they're higher energy than all the other derivatives, a lot of the time this is kind of an alternative to chlorides where we could just make the anhydride and then let it drop down into whatever derivative we want. So again, you could take the acid, dehydrate it with a few different options. P2O5 is probably the easiest one to remember, I guess. And then get this, and then from there, get the other derivatives that you want. And you pretty much just have to bring in something that looks like the other half of whatever derivative you're trying to make, and it should work okay. So examples are start out with an anhydride, react it with an alcohol. What derivative am I going to get out of this? Ester, right? I heard someone say psst, so I think that sounded like ester. I can only hear a little bit from here, but okay. Okay, so yep, we're bringing in something that looks like the other half of the ester. So that's the OR group, and then the H just comes off. What byproduct am I making out of this? Based on the leaving groups that I'm dropping this bit, I'm dropping this H, so I'm also making a carboxylic acid byproduct. And we know that this could do Fischer esterification with the ROH as well and make like a second equivalent. It's just not going to be as fast as the anhydride is. So it's just much slower, and so usually we're just going to assume that the reaction stops before it has a chance to make much of the ester off of that carboxylic acid. Especially since we're not really doing this under Fischer esterification conditions. Like, since this is less reactive, we need usually heat and like an acid catalyst to make it go in any reasonable amount of time. Okay, the good news is that unlike when we did this with acid chlorides, we are not making an HCl byproduct. This is actually a pretty weak acid that we're making as a byproduct, so we don't even need pyridine to sort of deal with the consequences of cleaning that up. So in this case, you don't actually have to write pyridine or any sort of sacrificial base on there. You can get away with just taking the anhydride, throwing in some alcohol, and boom, you're done. So that is kind of one benefit over using chlorides, is the byproducts are not so nasty. Okay, similarly, you can take an anhydride and react it with the other half of what would become an amide and get the amide that way. And again, you're not going to need anything to soak up the HCl. I guess you might lose a little bit of the base to the carboxylic acid byproduct. But I think the equilibrium is close enough to even that it's not enough to sort of burn through like half the equivalence of the base like it would be with an acid chloride. Okay, so both of these groups, anhydrides and acid chlorides, there's not really any heat required. You pretty much just throw in the other half of what you're trying to make and it goes to the products pretty quickly and easily. So these are probably like the two best options for making whatever derivative you want. On paper, they're totally interchangeable. I guess it just comes down to whether you can remember P2O5 for making anhydrides or SOCl2 for making the chloride. Okay, questions about either of those groups? Yeah?
How do you determine if we're going to get the acid or the carboxylate as byproducts?
So it depends on what conditions we're in. I guess in this case we have neither acid nor base around. So you can probably assume it's going to be neutral, in which case it's going to favor just the neutral like carboxylic acid product. If I did have a little bit of base around, like say I was using pyridine, then this would probably get deprotonated. So yeah. Okay. Other question? Yeah. Oh, so I guess because this one is an acidic group, you could do a wash with like aqueous base, pull it into the aqueous layer, and then this one would just stay in the organic layer more of the time. So yeah, good tie into lab. Thanks. Okay. So if there's, sorry, stretch or question up there? Okay. All right. So I'm going to move on to the next category of derivatives, which is much less easy to get to anywhere from. So reactions with esters. So much less reactive, but you can still do stuff with it if you're patient. So we can, if you bring in an amine, you can get from the ester to the amide. Again, we're bringing in something that looks like the other half of what we're trying to make here. This is really slow. I don't remember how much the book says about it, but you would be waiting around for like a long time or just cranking up the temperature on this thing trying to make it go. That's one option. Or one that actually does go in sort of a not too terrible amount of time is this thing where you start out with one ester, you bring in a different alcohol, and you make a new ester out of it. So you're sort of kicking out the alcohol from what used to be that side of the ester. Okay, so this one gets a little bit of a shout out because this is actually called transesterification. And this actually does show up in some reactions, particularly I think there's a couple of different polymers that get made. So like this is an ester group. If you have something with a lot of different esters along the chain, it would be a polyester. And some polyesters end up like financially it makes the most sense to do it by transesterification. But I don't remember offhand which ones they are. So, okay. So that's pretty much the only detail that we're going to go into on this. I guess you can catalyze it with acid or base, and that'll speed things up, but then you have to be careful about, are you going to mess up the protonation state of, for instance, the amine if you bring in acid? And yes, you are, so it's sort of a trade-off of like finding the right pH to do it at. Question?
What would like equilibrium look like on this? Because they seem to be the same.
Yep, yes, so you're totally right. If we just threw in equal quantities of everything, it would probably like equilibrate somewhere in the middle. But we can just saturate this thing with the new alcohol that we want and just force Le Chatelier to drive it over to the right. You can also do it by, like if this new ROH happens to have a lower boiling point, you heat it up and this distills out as the reaction goes, and then that sort of forces it to stay on the right anyway. Yeah, but yeah, there's no like huge benefit driving this thing. It's just fiddling around with stoichiometry at that point, pretty much. Mm-hmm. Yeah.
So the difference in speed because of the sterics of the markers of the nitrogen? The second one, or are they similar in speed?
I think that and maybe also just nucleophilicity of the N versus the O, but I'm not 100% sure about that. Yeah, I might have been overplaying like how slow the ester to amide thing is. Like, yeah. Off the top of my head, yeah, I'm not like totally sure if there's any inherent bias for one over the other, except that one has the two R groups that might be slowing it down sterically. So, okay. Any other questions about these two? Yeah, these are probably like the least useful ones out of this set just because, you know, you can do them, but acid chlorides and anhydrides are way more useful in a synthesis. Okay. So one last one in sort of functional group interconversions. And that is, we haven't really looked at how to make amides from acids. And there's a reason for that. So based on all of the patterns that we've seen before, we should expect that you take a carboxylic acid, you react it with an amide here, and you get this amide out of it, right? Because that's kind of the same pattern that we've been seeing for everything over here. The problem is that this is the only combination we've seen where not only do you have an acidic proton, you also have a base for the other reactant. And so rather than doing the whole like fundamental mechanistic steps where this goes in, attacks the carbonyl, kicks up, kicks down, boots out the leaving group, plus or minus some proton transfer steps, this is a case where it's actually much faster for this thing to just come in, rip off a proton, and call it a day. So I'm going to put an X through this for now, but I'll come back and add some more information about that in a second. What's actually more likely to happen is this thing just takes the easy proton transfer option and makes this instead. Okay, so it turns out you can actually force this to go to here if you add lots and lots of heat. And wait a while. but it's several hundred degrees, and at that point you're risking like doing some weird side reactions on whatever the R groups are. So this is generally not a great idea. So given that we can make amides pretty effortlessly from the acid chloride, basically like that kind of thing that I covered over there where you take the acid to the chloride to whatever other derivative you want, that's probably going to be the much safer option for making an amide. Okay. So, yeah, I guess as sort of a default rule of thumb, you can't go wrong with the acid chloride, but you can easily go wrong with some other options here. So, okay, questions about that? Okay. All right, so that kind of wraps it up for interconverting between acid derivatives. The rest of this chapter is going to be a couple of different reaction categories that we've seen before, just specifically applied to carboxylic acids. One of them is something that you're doing in lab this week. Okay, so reductions we're going to do first. Okay. So we know that from the last chapter we can reduce acids to the one bond to oxygen form, down to alcohols basically, if we use what reducing agent? Yep, LAH. Because out of the two that we were pretty much using interchangeably before that, sodium borohydride and lithium aluminum hydride, only lithium aluminum hydride is strong enough to actually go for the smallish delta positive on the carboxylic acid. Turns out you can use LAH for pretty much everything else in this chapter too. So, for example, if you start with an ester, again, just like always, we're going to use LAH as a separate step from the water workup, because if we try throwing these two in together, it's going to be very exciting. Not in a good way. All right, so I didn't really go through the mechanism for LAH reduction. It's pretty analogous to how it happens on aldehydes and ketones. I didn't even go into details in the notes, so let me just draw this out in case you're wondering. So what happens real briefly first is, just like it would for an aldehyde or ketone, it sort of reduces down the carbonyl. Like this, but actually that should be an O minus. So it does hydride addition first, like you kick this up to a single bond O minus. The difference is that here you can actually kick back down because you have a leaving group on there. And so you get temporarily to an aldehyde, which you can then send another hydride in to reduce again. So I guess just in case you don't remember how that looks, like here's a hydride attacking, that kicks up, you get to here, it kicks out the leaving group, you get an aldehyde temporarily, and then you attack again and it gets you to here. All right, so pretty much the big difference between this and the aldehyde and ketone stuff is that here we have a leaving group, so we do one addition, then it kicks back down, reforms the carbonyl and boots out the leaving group, and then we can do a second addition. And that's going to be a common theme for this and the next section of the notes. where we basically add something to the carbonyl twice when for aldehydes and ketones we could only have added it once. Okay. Questions about that? Yeah.
So, is it because of the ester, the OR, that you can't use NaBH4?
Indirectly, yes. So it's not because you have a leaving group, it's just because over here the delta positive is a lot smaller than it was for an aldehyde or ketone, and so it's just sodium borohydride just doesn't have the reactivity or the oomph, I guess, to just like send in a hydride and react. So it's just kind of down to like where aldehydes and ketones are on that reactivity kind of like timeline kind of thing that I put up at the start of the chapter. Like they're more reactive than esters, and these are just slow enough that sodium borohydride is not going to go after them at any significant rate, if that makes sense. Mm-hmm.
So when you have LAH, you're not forming like a intermediate, it's just attacking and like adding hydrogen?
You mean in terms of like bonding the O- to the aluminum temporarily, or? Yeah. Sort of. So like when I show O-, you can show that like complexed onto the aluminum. And I don't remember if the book goes into that level of detail or not, but I guess like for everywhere I show O-, you could show that bonded onto the aluminum, like stabilizing the charge temporarily. Kind of like when you have like an alkoxide, you could show it bonded to like the sodium that it's associated with, or you could just show it with a naked minus charge, and both are sort of accurate, I guess. So if that makes sense, yeah. Okay. So questions about this one? I guess like, yeah, depending on what level of detail you want to go into with what's happening with aluminum, this is sort of like a incomplete mechanism. So this is more like in case you're wondering what the key parts of what's happening are, this is what's going on, but I wouldn't actually test you on this, especially since I didn't include this in the notes. Okay. So amides, you're going to see a similar thing. So hydride can go attack that carbonyl. Which gets you to here. In this case, you actually end up having, okay, I didn't include the mechanism for this one in the notes either, and I'm wondering if I want to go into more detail or if I have time to do it. Yeah, why not? I think I got time. Okay, so in this case, you actually end up having to make a choice of, do I kick out the oxygen or the nitrogen? Because here it was oxygen versus oxygen, and so it's reasonably close to sort of equivalent. But in this case, it ends up being the case that, okay, so I guess in this case, showing the aluminum getting involved is pretty useful. Because you can actually turn the oxygen here into the leaving group. And you get to something that looks kind of like the, oh, and I guess I should show that H explicitly too, since that's what we added. So you get to something that looks kind of like the imidium intermediate from when we're doing like imine and enamine formations, which is also going to react kind of like a carbonyl would. And so you're still doing the same kind of overall reduction steps where you go from 3 bonds to electronegative atoms down to 1 bond to an electronegative atom, just like you did for the ester here. The difference is that that 1 electronegative atom that's still on there turns out to be the nitrogen instead of the oxygen, which is not what we would have predicted from looking at the ester mechanism up here. So overall for amide reduction, we are going amide to amine, not the alcohol like we would expect. All right, so again, this is not in the notes. There's a little bit more stuff that I'm kind of glossing over, but that's just more if you're curious what's going on here. This part is in the notes, so this would be fair game, but we're going to start with LAH. We're going to do a water workup, and then that gets us an amine. The problem is if we just do the acidic water workup, given that we know amines are basic, that's going to leave us with the amine in the wrong protonation step. So for this particular case, we're going to have to add a basic water workup after that. So we do acid, then base, and then all of the lithium aluminum hydride is neutralized and the amine is in the right protonation step. Okay, so questions about that? Yeah?
So the differences in these just based off the ability of the leaving group, the NR2 versus the OR?
Mm-hmm. Yeah, exactly. So it's just kind of kicking out a nitrogen with a negative charge we know is not as favorable by pKa. And so kicking out the oxygen, especially if it's stabilized on the aluminum, is a better way to go. So, yeah. Mm-hmm. Say again? Oh, down here you mean? Oh, so if we just stopped after step 2 here, we wouldn't be getting this. We'd be getting this instead. And so I would just want to clean that up by doing a mild base and washing that proton off. So, yeah. Okay. So other questions about that? Okay, cool. Alrighty, so I guess both of these esters and amides are less reactive than aldehydes and ketones. So as kind of the summary here, this is why we need lithium aluminum hydride, just like we did for acids. So this is why we have to bring in the big guns for reducing it with lithium aluminum hydride. What we're going to look at now is the other end of the acid derivative spectrum, chlorides and anhydrides, which we now know are more reactive than aldehydes and ketones. So we can get away with a lot of different options there. Okay, I guess I don't really cover anhydrides in this section. I think I'm going to stick to chlorides because I know for sure that these reactions work. I'm not sure how great they are on anhydrides. So we can actually use weaker reducing agents here. Okay, so one of these that we're going to look at is actually a relative of the Lindlar catalyst. So we can actually use, excuse me, sorry to deafen all of you, jeez. So we're going to use a catalyst that's kind of like Lindlar. It's based on palladium on carbon, but with some additives thrown in. And for this particular case, those additives happen to be quinoline, which is this polycyclic aromatic thing with a nitrogen in it, and sulfur. So it's another type of poisoned catalyst. It's poisoned and weakened enough that it can go after this easy, highly reactive acid chloride and reduce that down, but it can't go any further past that. So it's so weak that it'll react only with acid chlorides and not with the aldehydes that we've seen. So this combination is even weaker than sodium borohydride, in other words. Okay, so if it were as strong as sodium borohydride, we know that we couldn't stop here. We'd have to reduce down to the alcohol, but it can't even manage that. Okay, so that's one option. Another one is a seriously messed up version of lithium aluminum hydride, where we take, well here, let me write it on the arrow first and then draw it. So it's lithium aluminum, a single hydride, and then 3 terp butoxides. So that's going to look like lithium plus aluminum with an H, and then terp butoxide, terp butoxide, terp butoxide. So basically they've taken lithium aluminum hydride and sterically hindered it like crazy by sticking on 3 terp butyl groups onto it, and now it only has a single hydrogen to reduce with. So like you would expect, this tries to react with like lithium aluminum hydride would, but it just can't react very well. So it's reactive enough to go after the acid chloride and then stops at the aldehyde stage. So it's weaker than sodium borohydride is too. It just stops partway. Okay, so these are useful because I guess every other reduction that we've seen on acid derivatives, you start at 3 bonds to electronegative atom, and then you hit it with LAH, and then you go all the way down to 1 bond to an electronegative atom. So like LAH takes acids and esters to alcohols, or amides to amines. But this is pretty much the only way to stop partway, drop down from 3 bonds to 2 bonds. So if that's like the oxidation state you're going for, going to it via the acid chloride plus some super weak reducing agent might be the best way to handle it. Or the other option is, move the camera here. Or you could just reduce it all the way and then oxidize it back up a bit. So this is, I guess, a way of doing it that doesn't require you to remember a bunch of new reagents, but like if you take the acid, just hit it with good old LAH, H3O plus, get the alcohol, and then if you just hit that with PCC, then you're pretty much accomplishing the same thing. So either you overshoot, go down from 3 to 1 bond, and then back up to 2 in a controllable manner, or you can make the acid chloride and do it in one step. On paper, they're totally equivalent, but you might have a preference for doing it one way or the other. Especially like on these molecules, it totally doesn't matter which option you pick. But if you've got like a lot of other delicate functional groups in the molecule that you don't want to mess with, like maybe you have some other OH groups somewhere else and PCC would screw those up, then this would be a bad way to choose, a bad way to do it. Okay. So other questions about that? Okay, cool. All right, so last category of reactions is the one that you're doing in lab this week. So reactions with organometallics. Okay. So the one that you guys are doing are esters with Grignards or organolithiums. And this is kind of similar to the lithium aluminum hydride thing where you add once, kick out a leaving group, add a second time. And if you happen to have like a diester like some of you have for this lab, you actually kick out 2 leaving groups and add a third time. But I'm just going to show it with regular esters here. Okay. So add the once. Kick out a leaving group. And now you've sort of reset the carbonyl. And you can do the same thing again. So like that. And then if you do a water workup, you can get an alcohol out of it. Okay, so I should add this to the notes, but in terms of like picking this out during a synthesis of like this might be an efficient reaction to use for where you're trying to go, kind of a tip-off that this might be a good idea is if you've got an alcohol with 2 identical R groups attached to it. So for example, you might say, if I ask you to make this from something with like 7 carbons or fewer, you've got 2 identical R groups here. So maybe you can do it in the fewest possible steps if you just bring both of them in as Grignards, attacking an ester here. All right, so I'm going to start off with an ester. Does it matter what this part of the ester is out here? Nope, because it's going away like pretty much immediately. So I'm just going to call it R. And then plus 2 equivalents of CH3 MgBr. And that would be just a one-step reaction to add both those 2 R groups on at the same time. Okay. And then, I might have to make this from whatever precursors moving backwards depending on what the exact conditions of the synthesis problem are. But this is kind of a good way to make multiple things happen at once. Okay. Questions about that? Okay, cool. So one other option in this chapter, or in this section, is all right, so I guess the whole deal with Grignards and esters is you add once, you make another carbonyl, which is an aldehyde or a ketone, and then there's no stopping it. We know Grignards go for aldehydes and ketones. It's just going to add a second time. If we want to stop after one addition, though, we're going to have to dial back the reactivity on the organometallic because it's going to, go for whatever product we make if it's too reactive. So the way that we can do that is cuprates plus acid chlorides. So cuprates, so just to keep it parallel to up here, cuprates and acid chlorides only adds the once because cuprates are reactive enough to go after the acid chloride, which is like the super attackable electrophile. But not enough to go after the ketone or aldehyde that they make. So like pretty much any kind of organometallic could attack this thing. It's real attackable, real electrophilic. So we have our cuprate here. Attack once, and it starts out looking like, I have a typo in the notes. I show it kicking out an OR group when that should be a chlorine. All right, I'll have to fix that. Okay, so the O minus kicks out the chlorine, and then you get to here, and then cuprate is actually too weak. To attack this, so at this point you just stop after one addition. Okay, questions about that? Okay, cool. All right, so that actually wraps it up for this chapter. There's a lot of stuff in this chapter, a lot of reactions overall, but as long as you look for like the common patterns, it's really just kind of the same theme happening over and over and over again, just with slightly different details each time. Okay, so I'm going to do a synthesis problem in the last 5 minutes. Okay. So I want to convert that alcohol into this amine. All right, so I guess I didn't explicitly say this in the notes, and we won't cover why certain options are a bad idea here until we get to the nitrogen chapter in a couple chapters from now. Your first glance looking at this might be to think, convert this OH into a leaving group like a tosyl, and then have nitrogen come in and do SN2 on it. Turns out that has some unexpected consequences that are going to make that not work. Okay, so instead, a better option is actually going to be, we know that we can easily make a single carbon-nitrogen bond if we turn it into an amide, or if we go through something involving an amide. So maybe sort of our key steps should look like some kind of acid chloride maybe. So the way that we're going to make this carbon-nitrogen bond is by making it as an amide. Okay, and I guess since we haven't covered this chapter yet, if I gave this to you as a synthesis problem on an exam, I would have to say explicitly like SN2 is not going to work here, try something else. Otherwise, that wouldn't really be fair until we cover it as part of chapter 23. Okay, so given that making this as an amide is kind of the best way to go, now we have to figure out how to tie this into the starting and ending points to actually get an overall synthesis that works. Can I go directly from here up to here? So, yeah, this reaction here, amide goes to amine if we use LAH. So that actually is going to work okay. Okay, so that end of the synthesis we've got sorted out at least. We can't go directly from here to here, but we can go from the acid to the acid chloride. That's just SOCl2. How can we go from here to the acid though? Jones, yep. Or, you know, whatever way you want to write various different oxidation agents that we've seen. Okay, so I guess this is sort of like, even though we're staying in the same oxidation state start to finish, we start with one bond to O, we end with one bond, or start with one bond to electronegative atoms, end with one bond to electronegative atoms. It turns out that a safer way to control the actual, like, what's getting added there is to, like, sort of go up and over, like we go up to a different oxidation state, we fiddle around with exactly what's involved there, and then we reduce back down at the end to sort of get pretty good control over exactly where the nitrogen adds and when. Okay, so questions about that one? Yeah? So PCC, if I did that, it would actually stop at the aldehyde. So let me just draw that as a separate piece. So in this case, since we're specifically trying to access carboxylic acid chemistry, Jones is the good way to go. Yeah. Thanks. Uh-huh. Oh, good question. So it's pretty much just going to be the amine there, and then we need some sacrificial base, ideally. So like pyridine would be good. Mm-hmm. Okay, thanks. All right, so that ends this chapter. I'm going to post the notes for the next one online, and then we'll pick up there on Friday. Hi.
So if I went from